On the other hand, if the moment was aligned perpendicular, so just flat, then it would not feel any force at all, which kind of makes sense.
It makes sense that if you put your magnet with the north and south parallel to the magnets, that there will be no force. Is that how everyone? I can't believe this.
It's like halfway between feeling a force upwards and feeling a force downwards. So it just feels no force at all, and it would end.
Is that all? I'd like to see someone put a magnet in between two giant magnets so perfectly that it doesn't go to either one.
Up in the middle. Now, of course, there's many other orientations that this could have. So if it was a little bit like this, then you would expect that instead of feeling no force, it would feel a little bit of force, but not enough to make it go all the way up here.
No, it would rotate it so that it was straight up and down, just like every one of these other ones, and then it would go whatever, north go to south and south would go to north, just like any magnet on the planet.
It would just be enough to get somewhere in between. So
she's saying she's throwing magnets through these two magnets, and she thinks some of them aren't going to be affected.
And similarly for that magnetic moment. And by the way, it could of course also be aligned this way, so that it's completely flat in the other direction. This would also just result in it like ending up sort of here, because it doesn't feel any force up or down.
Is that, if you have your north and your south here and you have them perfectly in between these two magnets, is that what happens, huh? Doesn't feel any force, huh? Alright.
It only matters for this Stern-Gerlach machine how up or down the orientation is. It doesn't really matter how into the page or out of the page it is. So this machine is just measuring how much is the magnetic moment of this charged particle pointing up or down. Now, physicists imagined that electrons would act a lot like they were spinning on their own axes. And so, if we do this Stern-Gerlach experiment, we know what to expect. Well, since these axes would probably be all randomly aligned, there's just as much chance that you would end up going upwards as you would downwards, and everything in between. And so you would expect that when you put these electrons through this machine, they would all just sort of end up spread out.
Is that what you would all think? You throw a tiny magnet in between two giant magnets, they just spread out. They wouldn't get 50% to the north and 50% to south. No, okay.
Something like that. But that, of course, isn't what happened. What actually happened is that maybe the first electron went all the way to the top, and then the next may have ended up all the way at the bottom. Well, that's a bit of a coincidence, but let's keep going. Then the next one might have also ended up...
Is she retarded?
Exactly at the same spot, right at the bottom, and maybe the next one ended up right at the top, and then another one at the top. So you end up with the electrons grouping up into just two spots. The first spot aligning with all of the electrons having the maximum spin up, or all of them having the maximum spin down. And there's nothing in between.
Yeah, because the north goes to the south and the south goes to the north. You reoriented your magnets, you moron. That's what happens when you throw a little magnet in between two giant magnets. All of them get stuck to the, half gets stuck to the north and half gets stuck to the south. Now they're all oriented up and down with their north and south, okay? So you made them all the same.
That seems really, really odd. But it's kind of just like these electrons. It's not the case that the electrons happen to have magnetic moment exactly facing up or down. They could have had all kinds of momentum, but when they go through here, it's like the measurement forces them to choose.
Is that what happens when you throw a little tiny magnet between two giant magnets? Is it like the machine just forced them to choose? Yeah, it forced them to choose an orientation so that the north and south went with these two giant magnets.
Do they want to be fully up, and do they want to be fully down?
Is this insane?
In fact, mathematically at least, these two systems are almost identical. I wanted to discuss whether electrons really are spinning on their own axis like
I didn't think so, but after this, yeah, they're freaking spinning, you moron.
this. I mean, this was the interpretation of the Stern-Gerlach experiment at the start, but afterwards people started questioning it. So one of the reasons I've heard people question it is that electrons should be point particles. They don't have, like, physical extent. They're infinitely small, and so how can they spin around? I don't know where that's coming from, to be honest. I don't think that quantum mechanics says at all that electrons are point particles. In fact, in quantum mechanics, electrons are fairly spread out. But I still don't think that that explains spin. So it's not like because the electron is spread out into a ball like this.
Instead of just going with all the experiments and all the evidence telling you, if I knew all this experiments and things and laws were, why don't you just go with the evidence? Why do you have to force your beliefs on physics? Like, what the?
Then that ball rotates, there is this thing called spin. The reason why I say that is because the spin of an electron, so how much of this intrinsic angular momentum it has, is unrelated to how spread out its quantum wave function is.
See, that's what's going on here, okay? This wave function, it's a math thing, and they're shoving it down our throats, I see now, okay? I can't believe I believe this crap. An electron, you just can't see it, apparently. It moves too fast and it's too tiny. So to explain that they can't do something, oh, no, I can't, no, it's not that I can't do it, it's a wave function. It's just all blurred all over the place. Oh, okay, is that why, huh?
So even if it's a really big wave, or if it's a very small wave, it doesn't really affect its spin. It always has the same amount of spin. It's just...
Yeah, because no matter what you do with a magnet, whether you look at it from one frame of reference, you look at it from another frame of reference, you drive by it, whatever, it's always going to have the same magnet, magnet field, you idiot.
It's the direction of that spin that's allowed to change. So then it doesn't make sense for the spin of an electron to be a result of how spread out the electron is and how that stuff is moving around in space. That actually just goes straight into the angular momentum, which, remember, does exist in quantum mechanics. There is just regular old angular momentum for electrons, and electrons can have it when they're going in circles, like when they're going around an atom. But this intrinsic spin is completely unrelated to what the electron is doing in space. And so that's what makes me think it truly is a different property to angular momentum, and it probably doesn't represent a ball spinning. Let's do an experiment.
Yeah, but you're someone who thinks you can throw a magnet in between two giant magnets, and they're just going to float through depending on, where you orient the north and south. You are freaking moronic.
We're going to start all of these electrons off with their magnetic moment facing down. Well, how do we actually prepare all of our electrons like that? Well, to prepare the electrons in this state, all we need to do is get a Stern-Gerlach machine and send these electrons down the machine. Now, half of them are going to get pulled upwards and half of them are going to get pulled downwards. Now
we all understand, right, that if you throw magnets at random whatevers, 50% will go up and 50% will go down. But how will they go down? They will rotate, and if this is the south giant bar, all the norths will come down and hit onto that. They'll all be oriented in the same exact way, right? And then these magnets will be taken up air, and they'll be oriented in the same way. North will go to the south, and south will go to the north, so that they are all, these bottom ones will be oriented like that, you know what I mean? And these ones up here, they will be oriented the opposite way, just like any magnet. Any magnet. Why would she think that you could throw a magnet through two magnets? She doesn't. I don't understand how these people have millions of people clapping for them, and all I get is people telling me I'm a piece of crap.
All we do is we discard the ones that went down, and we just keep the ones that went up. And now, because of the post-measurement rule, we can be sure that their state is up. It's not oriented up and down. Instead, it's oriented left and right. And so
now the north and south are exactly like this. So if 100% of them are like this and they put it right down the center here, what's going to happen? 50% are going to go that way and 50% are going to go that way, right? Because that's what magnets do. 50%. If they're all randomly chosen, 50% will go one way and 50 the other way. If they're all oriented parallel to the two, you know what I mean? North and south is parallel going in. Yeah. Is this woman is like, what the?
Now the electrons again have to choose whether to go left or to go right. Remember that for a Stern-Gerlach machine, the electrons can't just choose to go right through the middle. They either have to go to the left or to the right. And so 50% of them will go either way. And the reason it's 50-50 is because if you imagine an electron that's oriented down like this, it has no particular bias towards left or right. And so both of those are sort of equally as good. And so half of them go both ways. And again, we are going to discard the ones that didn't go the way we wanted. So we're just going to keep the ones that went right.
Again.
And so now we know these electrons are all oriented to the right.
Yeah.
This is really similar to if...
It's not a different quantum state. Your magnet turned. You oriented your magnet north and south to be in one direction. And now you're going to make it parallel, the north and south, to your new machine.
A very similar thing is going to happen with the spin. Instead of these electrons acting the exact same way that the original electrons will have, they're actually going to act completely different. They're going to split 50-50. Half of them will end up at the top, and half of them will end up at the bottom.
They're doing the same thing. They're always doing the same thing. So they're magnets. You said that everyone is emitting their magnets, electrons. What do you expect them to do, you moron, when you make the north and south go through and you put them exactly in between? 50-50. What kind of moron are you?
Now this result, similar to in the light case, can only be explained by measurement collapse. To figure out what's going on in this experiment, we need to be able to talk about the quantum state of an...
So this is what quantum collapse is. Turning your magnet to another direction. That's a different quantum state, huh? Oh, this makes sense.
Can only be explained by measurement collapse. To figure out what's going on in this experiment, we need to be able to talk about the quantum state of an electron with spin. First, let's deal with the easiest case. We have an electron that has already gone through a Stern-Gerlach machine just now and ended up up.
Okay, so that means north is up and south is down.
So we want to represent this state as a quantum state. Remember, our first rule of quantum mechanics is that every quantum state is a vector. So we need a vector that represents this state. Well, this case is fairly straightforward. Let us draw this vector that represents the state of this electron as this arrow.
Keep in mind, this is a magnet with north and south, and she's going to plot it down like we can't figure out what north and south means.
And we're going to call it up.
Yeah, don't call it north.
Imagine that we put this electron
sane.
through the Stern-Gerlach machine, and instead of getting the result up, the electron went downwards, and so this is in state down. How should we draw this state?
I would draw it down because this is north and this is south. You moron. If I knew that electrons were little magnets, this is insane.
You might think that the best way to do it would be to draw it downwards, and that would make some sense. But actually what we're going to do is to draw it this way.
Yeah, you want to do something that makes sense.
Why would we do that? That's because, remember, this is a mathematical representation of the actual physical situation. And what we want to, encode in this representation is some relationships about these different states. So, for example, up and down are opposite states to each other. When you do a Stern-Gerlach experiment that's aligned in the up-down direction, each electron has to choose whether to go up or to go down. And it can't,
She's literally talking about a magnet. Okay, they all admit it. She admits it. They all admit it. They don't admit why, but they say it's intrinsic. I'm not debating whether the electron spins or not. If it has a magnetic field, you moron, that makes it a magnet. If that means it has a north and a south. That's what up and down is, you idiot. You said it. All the physicists are saying it.